So the last video cut off there. Not sure why the document camera keeps doing that, but we were about to cut off anyway, so it's not really a big deal. So where we had left off was talking about the neurotransmitter being found in the synaptic knobs, and it's found in vesicles. And we need to get those vesicles containing the neurotransmitter out. And this is going to be very much like exocytosis. It really is just exocytosis, just linked to electrical activity. And if you remember with exocytosis, we had vesicles containing whatever kind of secretion we're talking about. And they would fuse to the inside of the cell membrane and then essentially just kind of turn inside out so that whatever was contained inside could be released to the outside of the cell. And that's what's going to happen when we're releasing our neurotransmitter. So we have our action potential come down the axon, it hits the synaptic knobs, and then when it does, that action potential is going to trigger the opening of our voltage-gated calcium channels. Those calcium channels open, calcium comes into the cell, and calcium helps those vesicles diffuse to the cell membrane, allowing the neurotransmitter to be released. Now, we also have things that are called neuromodulators, and neuromodulators are not neurotransmitters, but they're sort of similar in that they're going to affect the function of a neuron in some way. And they can do a couple of different things. There's things they can do systemically, like just generally cause just depolarization of your axon hillock there, making it easier to have action potentials, or they can block substance P receptors, which is how you transmit pain. So they block pain, essentially. Or they can act more locally on a particular neuron by either inhibiting the release of neurotransmitters, so slowing it down, or facilitating it, speeding it up, making it easier. And they can do that via these two different mechanisms. If they're going to facilitate it, it's called presynaptic facilitation. And they'll open calcium channels, so that it's just easier to get those vesicles fused to the cell membrane and release the neurotransmitter. Presynaptic inhibition will do the opposite. It'll close those voltage-gated calcium channels, so it's harder for those vesicles to fuse. Now, before we get to what happens once that neurotransmitter is in the synapse and how it's going to affect this second cell here, this postsynaptic cell, I want to go over one little thing called Ohm's Law. And this is dealing with the EPSPs and IPSPs and how they travel or diffuse along the cell membrane. What this is just talking about is how fast the current's going to flow and how strong that current will flow. And if there's any resistance to the flow, like friction, there's membrane friction that kind of slows down the flow of these ions as they diffuse along the cell membrane. That's all Ohm's Law is talking about. So it's an equation, but it's a very simple equation. It's not really difficult at all. It's just saying that the current of the graded potential, so the strength of the graded potential, or the flow, not the strength really, the flow, how fast the flow of that graded potential is directly related to the voltage. So how strong that graded potential is. Is it a very strong, very big difference in the transmembrane potential, or is it a smaller one? And then it's also inversely related to the resistance, so how much the membrane is resisting the flow of that graded potential. So in the equation, I is the current, so how much or how fast does that graded potential flow. V is the voltage, so the strength of it, and then R is the resistance. So I is equal to V over R. If you increase the voltage, so the bigger this number is, the bigger this number is going to be. They're directly related. So stronger current has a faster flow. That just makes sense. If you increase the resistance, on the other hand, these are inversely related. Resistance is trying to slow down flow. So resistance going up is going to decrease your flow. So it just sort of makes natural sense that these are opposite. It's resisting the flow. This one is encouraging the flow. Okay, so let's move on. Let's go into what our neurotransmitter is going to do to this cell. Remember that this cell, so I put what we call a membrane-bound receptor here, and that's typical for neurotransmitters. Most of them will have receptors that are membrane-bound. Remember that this neurotransmitter is going to have receptors here that are specific for it. So let's say, for example, that this is acetylcholine, which is abbreviated as ACH. So that's the neurotransmitter. This receptor here will be a cholinergic receptor. You can kind of see the link between those two words. Acetylcholine binds to cholinergic receptors. This just means that this receptor can only bind acetylcholine, and then it'll have some sort of effect within the cell. And we're going to see the different kinds of effects we can have in a second. We also need to realize that the neurotransmitter isn't going to just stay in the synapse forever, just consistently or continuously binding to these receptors. Then every time you release neurotransmitter, the effect would never stop. We need to be able to break it down, and each neurotransmitter will have various methods of being broken down or taken back up, what's called reuptake back into the synaptic knobs to be recycled. In the case of acetylcholine, we have an enzyme called acetylcholinesterase. Acetylcholinesterase. And that breaks down acetylcholine. It'll break it down into its component parts, which can be taken back up into the receptor or into the synaptic knob and turned back into acetylcholine. You've probably heard of these in terms of like antidepressants. For example, a serotonin reuptake inhibitor. So let's pretend this was serotonin in your brain. Serotonin is a very calming, happy neurotransmitter, so a lot of times if a person is depressed, it's because they just don't make enough serotonin, so they don't have enough happy neurotransmitter. So you want to not break down whatever serotonin you have. You don't want to take it back up again because you're not going to release it fast enough. You want to leave it there so it can continue stimulating. So a drug can protect, essentially, that serotonin, then leave it in the synapse right there. Okay, so let's move on. Let's look at two of our common neurotransmitters. We're going to use acetylcholine, and we're going to use epinephrine/norepinephrine as our examples for how it might behave in the synapse, so how it's going to affect the cell. Is it binding to a membrane-bound receptor? If so, what is that going to do inside the cell? Or there's also the possibility of receptors inside the cell, although there's only one neurotransmitter really common neurotransmitter that does that. So let's look at the different ways that this neurotransmitter can affect the second cell, the postsynaptic cell. Okay, so mechanisms of neurotransmitter action at the synapse. There are two main ways. They can bind to receptors inside the cell. In the case of this, they have to be able to diffuse through the cell membrane, which is not really that common for neurotransmitters. Nitric oxide can do this because it's a gas. When you get to hormones in AMP2, hormones are going to have the same ways of acting on their target cells, and you'll see a bit more of this because some hormones, fat-based, lipid-based hormones, can get into the cell. So we'll have some examples of that. Or we can have membrane-bound receptors. This is what we're really going to be looking at for how our neurotransmitters act. So in our case of membrane-bound receptors, it just means that the receptor is found on the membrane. There are two options then for how that receptor is going to be structured. It might be a chemically gated channel. So let's just say it's a sodium channel that's chemically gated, and then the neurotransmitter binds to that chemically gated channel. It opens the sodium channel, in goes sodium, and you're having a depolarizing graded potential. Or it could be something called a G protein coupled receptor, which involves something called second messengers. In this case, the neurotransmitter will bind to the receptor, which has a G protein on the inside of the cell stuck to the receptor, which is why it's called a G protein coupled receptor. And that G protein, once it's activated by the neurotransmitter binding, will set off a series of chemical reactions that'll happen within the cell. And those are called the second messengers. So I'm going to take a pause on this video before it cuts me off, and I'll start up with the next video, which will go into our second messengers.